Hello everyone, welcome back to the channel. So today we are gonna use a machine learning, a supervised machine learning model, which is a linear regression. So I'm gonna use a diabetes data set. So this is like we are gonna predict like whether the person is how likely to get this diabetes. So this is an inbuilt data set I'm using. I don't think so, which has a real meaning, but this is how we can work in a real world data set. If I have a data set with the details of a person, then we can predict how likely he get a diabetes soon based on the features. So this is a simple data set, which is an inbuilt data set from sklearn. So I'm gonna use this data set and I'm gonna uh, build a linear regression model. So it's like a little bit interesting topic. So this is my first video on machine learning models. So I'm importing all the necessary libraries here, like NumPy, Pandas, Matplotlib. So this time I wanna this is model selection. I just wanted to split the existing data into a training set and a testing set, so that I can train the model, and the remaining testing part I'll test as soon as I'm done with the training. Then I'm gonna test the model with the testing set. So that is where I imported sklearn dot model selection. So train test split. Then I'm using linear regression. So linear model, importing linear regression and the matrix to evaluate the model performance. So I need to import mean squared error as well as R2 score, and also absolute mean square also I have to, this is enough actually. So these two matrices are mean squared error and R2 score is enough to evaluate the model, how good the model is built and how it is performing. And also I included a new data, also new features. As soon as I mean the model is built and I'm gonna test it with the new features, so that how the machine is predicting with a new data set. So I'm importing this load diabetes dataset from sklearn.datasets. So let me run this so that I'll be able to use all these libraries properly. So if I wanted to load the dataset, so this is all these things, this basic things. So why should I import train, test, split, and also how to import a model from linear model, and what are all the different type of matrix as per the model to evaluate the model, and also how to import inbuilt data sets from sklearn. I have covered all these things in sklearn tutorial. If you have any further questions, in detailed answers are explained there. So diabetes is equal to load diabetes. So this is, I'm just loading the data. And so if I wanted to see, so I'm preparing my data set pd dot data frame. So diabetes dot data. So that is what I just wanted to show. So here I named diabetes. So diabetes dot keys, so that we'll be able to see what are all the keys present. So this diabetes data set has this means entire data, and what are all the target variables we have, and what are all the frame description, feature names, and data file name, target file name, and a data module. So if I wanted to get all these things, just mention. So since I loaded the data set and I'm assigned this data set to a variable diabetes, right? So diabetes dot keys, then I'll be able to get the data set details. So here, since I just wanted to define the data set for further process, so I just wanted my data as diabetes dot data, and my columns are feature names. So this is how we can load the data sets from sklearn we can able to use. And this is my target variable. So this is progression. So before jumping further, let's look at the info of all the columns in the data set. So this data set has a age column, which is nothing but a person age. So we have around 442 entries, and I do not see any null values here. See, all the rows are filled with 442 entries. We do not see any null values, and all the d types are also good to go. All are float 64 only, because these are all numerical data types. So that is, we don't need to convert anything, we don't have to scale, because this is an inbuilt data set, so all the values are already scaled. And also we don't have to do any encoding part here, because we do not have any categorical variables. So we have all the details in a numerical format, and as well as already scaled. These values are already scaled. So if I look at the each and every feature, uh, so first, the age, which is nothing but age of the person, and the gender of the person. Next, body mass index of each person, and also BP. Blood pressure, so is often monitored in diabetic patients, as they are at higher risk for cardiovascular, right? So that is why this BP column is also mentioned for that particular person. And we have this S1, S2, S3, S4, S5 columns, S6, or various blood measurements that provides insights into the patient's metabolic health. For example, high LDL and low HDL levels are risk factors for heart disease, which is common among diabetic patients. So these columns from S1, S2, S3, S4, S5, S6 has a meaningful like value in the data set, so that it is depending on the progression. So this progression feature helps quantify how the disease is progressing over the time, which is critical for managing diabetes and planning the treatment. So that is what this is. This progression is nothing but a target variable for us. We are gonna predict the values, how likely a person will get the diabetes, so that he can consult the doctor and he can do the preventive actions. So that is the in detailed description about all the features and target variable. So that is where I assigned the data dot progression is equal to I'm assigning this diabetes dot target. So if I wanted to see the uh, first top 5 rows, how my data set is. So this is because you can see age could not be 0.03, and this gender is also could not be 0.05. So that is why it was already scaled. It was encoded and scaled. It is very good to feed this data to a machine learning model, so that the machine will predict without any, trouble. So that is why this inbuilt data sets are all are like the data is encoded and as well as scaled. So that is why we can see the columns like this. Age is with a point. That is why all the columns are in float format. So age, gender, BMI, BP, and this respective S1, S2, S3, S4, S5 columns, and the progression. How a person is likely to get diagnosed with a diabetes. So if I wanted to check the null values, however, I can get this information here like non-null, non-null. So out of 442 entries, so all the columns are filled with the data. We do not have any null values. So still, if I wanted to check, I can check like df dot is null dot sum will give me the number of mm, null values. So we do not have any null values. All the columns are filled. And if I wanted to look at the description of the data set, so this is how the count and also the mean age, standard deviation, minimum 25th quantile, 50th quantile, 75th quantile, and the maximum value among all these uh, columns. So this is how you can look at the statistics of a data set. Just give the data frame dot describe. It will give us a nice. So let me transpose it so that I'll be able to look at the data in a better way. See, so in these are my columns, and these are all my statistics like count, mean, standard deviation, minimum, 25th, 50th, and the 70th maximum. So that is how we can look at the statistics of this data set. Okay, and so just if I just wanted to visualize the relationships between uh, BMI, body mass index, and also the progression. So I just wanted to plot a scatter plot between two variables, BMI. So before plotting the scatter plot, let me look at the correlation so that we'll be able to see. Okay, it is small d. Okay, so here you can see which column is correlated. So body mass index, see, which is highly correlated with. This is my target variable. Just look at the values which one has high correlation. So here BMI has almost 0.5%, so which is highly correlated, as well as BP. So these two are highly correlated, and also this S1, also this S5. So so that is why I just wanted to plot this BMI first, because this is highly correlated. So I wanted to see the a person's body mass index as well as a progression. So if I plot this, then so this is the relationship between BMI, body mass index, and disease progression. So this is my body mass index on X label I passed, and the Y label is disease progression. So this is how the data distributed. So if the body mass value is increasing, uh, then the disease progression is also increasing. See, you can see a linear relation between these two columns. So as soon as the body mass index is increasing and the disease progression is also increasing, this is how we can see a correlation or relation between two features. Here I just took BMI and disease progression. So that is how we can look the relation between two variables within the data set, so to get an idea. Because here why I just took body mass index, because it which has a highly correlated, I mean high correlation with the target variable. My target variable is a disease progression, and out of all the features, this body mass index has the high correlation, which is 0.5 0.58, which is close to 0.6%. So let me divide my data into features and target variable. So features, I'm giving all the columns except progression, because this is what we are going to predict. This is a person how likely to get diabetes. So that is how we are going to predict it. So that is why I'm giving dot progression to y variable. Y is nothing but my target variable, and x is my input features. So that is why I passed features is equal to all the other columns, age, BMI, BP, from S1 to S6, all the other columns from here to here. And I assigned the last value because it is my target variable. So that is I assigned it to Y. Then I have to split the data into a training data set and testing data set. So that is where I have to use train test split. So X train, X test, Y train, Y test. Then train test split. I'm x comma y. I pass two variables input features as well as the target variable, and this time I'm giving a test size of zero point 0.2 because I wanted to split the entire data. 80% I'm using it for training, and 20% I'm using to test the trained machine model. And random state I'm giving 42. So let me run this and I'm using linear regression just because you can see my target variables are in numerical like float. So these are in numerical format. So I can use linear regression. So that is why I imported linear regression. So model is equal to linear regression I give, so that it will give us, because as per the linear regression conditions, only the continuous variables we can predict. So here we have the target variable has continuous variables. So that is the reason why I'm using linear regression. Model is equal to linear regression. And so if I wanted to fit the model, then model dot fit, I'm just passing x train and x y train, because I split the data into 80-20, right? So I'm just passing the 80% of data to the model so that the model will be fit. So I feed it this 80% of X train and Y train data. So model will learn the patterns if I pass this entire data. So we are done with this two-line syntax. We are able to build a machine learning linear model. Now I just wanted to predict the values. I'm done with the model. Now this is my model, a linear regression model, and I wanted to predict it. I already use 80% of the features and output variable. Now I wanted to test. This is X test. My 20% of data still there because I kept aside to test the model. So model dot predict. The syntax to use predictions is like model dot predict. I need to pass the variable X test. So the 20% of the data. So that is I am assigning to Y predict, because I have Y test values already there when uh, I mean the splitting the data. So already the original actual values, these are Y test values are nothing but actual values, and these are the predicted values. So now if I wanted to evaluate the model, so I have to evaluate with the mean squared error. Since for a linear regression model, so this is the evaluation method, mean squared error, and also the R2 score. So if I run this, so let me run this. So this is these are all my coefficients, and this is my intercept value, and this is the mean squared error 2986, and the coefficient of determination, which is nothing but R2 value. So anything less than one is a good fit. My model is I mean predicting good. So if I'm getting a R2 score is less than one, that means model is behaving better. That is how we can evaluate the model. And if I wanted to look at the how the actual values and the predicted values, how the machine predicted the 20% of the data. So if I wanted to plot y test, y predicted, and I'm just giving the color blue, and the plot y test minimum value, y test maximum value, y test minimum maximum, I'm giving this color red. So X label is actual and Y label is predict, actual versus predicted disease. So if I run this, so this is how you can see actual versus predicted disease scatter plot. You can see the just dots, how the data distributed, actual data as well as the predicted data. So you can see this is a perfect fit linear regression line. So you can see this line, this is a linear regression line. So if I wanted to have a better idea how the model is behaving with the data we fed, so I can get that information by plotting a line plot. So this is what I used. So I just wanted to use matplotlib here. I just defined the fixed size 10 x-axis 10 centimeters and y-axis 6 centimeters. Then I just wanted y test values and labels. I'm giving x actual, and the color I wanted blue. This is for y test. Y test is nothing but the actual values, and this is predicted values. This is I'm giving predicted, and color I am red. So whatever the red color is there, that is a predicted value, and whatever the blue line is there, that is for actual values. So this is I'm giving line, a dot line, red dot line for predicted values. X level I am giving some sample index. Y level I am giving disease progression. Title is actual versus predicted disease. So this is how the machine is performing. So you can see, so this my blue line is actual data, the data we have input, raw data, whatever we fed to the model, and the dotted red line is how the model predicted. So you can see almost similar behaving. We can see, so here almost it is increasing 10 and then decreased, then increasing. It is almost with the actual values only. So you can see a sample error percentage, that is a, mean error. So that is where we already calculated, and the R2 score is also we calculated, which is less than 10, which is a 44%, 0.44. So it is a good fit, and this is how you can see how the predicted values and how the actual values, the predicted values versus the actual values. So this is how you can see the line chart between actual and predicted values. And if I wanted to test the model, like I fed the raw data, I trained the model and also tested with the sample 20%. So I wanted to test the model with a new data set, no, which is not included in the original data set, so that we can see how the machine is predicting. So these are all my new values. So for age, I'm giving these data, and BMI, BP, S1, S2, S3, S4, S5, S6. So these are my input features. So based on these input features, I wanted predictions, the disease progression. So if a person has the age is something like this, BMI something like this, BP something like this, S1, S2, S3, S4, S5, S6, then what is the disease progression if a person has these values? So this is how we can predict prediction. Model dot predict, same syntax, and now I need to pass this new data. If I pass this new data, then model will predict. I assigned it to new predictions, so these are all my new predictions. So these are, so this is how you can test the model once you build. So this is how you can test the model with the new features. So I hope I have covered everything in this tutorial about linear regression. So starting from importing all the necessary libraries and loading the data set from sklearn, and how to see the keys from the data set. And also I explained each and every column in detail, and also there are no null values in the data set. And also when we looked at the stats of the data set, we'll be able to see how many, I mean, count, mean, standard deviation, minimum, and also quantile values, and the correlation. So correlation is very high for BMI, body mass index, and for progression. So we do not have any null values in the data set. And also I just segregated the data to features. This is how I selected the feature selection. So since it is a scaled data and which is already inbuilt data set from sklearn, so we do not have to work a lot. But when we have a real messy data set, we need to clean the data set first, we need to fill the null values, and also we need to select the features based on the correlation, how it is negatively correlated or positively correlated. So that is a real challenge, since this data set has all the values are scaled and also the encoded. So that is why we do not have to work a lot. It is a simple process. But whereas if you are working on a real world data without I mean a data set with the null values and with some like with some null values, then that is very difficult for them. So in future I'm gonna come up with a new data sets with some null values where we have to do some feature engineering as well as how to select the features, and also how to, I mean, converting the categorical variables to numerical variables by using one hot encoding, something like that. So we will cover all these things in coming videos. Since this is a very first video, I just took inbuilt data set so that we'll be able to have a proper idea how this linear regression will works. So I hope you are getting something out of these videos. So please don't forget to like, share, comment on the videos, and also please don't forget to subscribe the channel. Bye everyone. Thank you.